Welcome, physics friends, to 15.2 Part 2, which I've entitled Open and Closed Tube Resonance. What we're going to be talking today is about if you've got like a tube, and I have a tube right here. You might recognize this. This is a 40-ounce bottle. Maybe you've done something like this before, and maybe you've wondered, why does it play the note that it plays? Well, today that's what we're going to explore. Why does this bottle play a certain note? And it's not just one note. I can play multiple frequencies on here. Why does that work? How does that work? What's going on? And that's what we're going to be talking about today. So just to get us started, I got a couple of open and closed tube videos that I wanted to show you. This is an art installation. I don't know where it is. It's someplace. It looks like something Russia would have. But it's a bunch of tubes set up looking like a tree, and when the wind blows past those tubes, and it creates like a very eerie noise. The next one, how do you make a recorder from a carrot? Maybe you played a recorder when you were a kid.
Today, I'm going to show you.
So he's jumping through, you make some cuts, you drill some holes, put them at certain spots, and then when you blow on it, you can actually physically make a pretty legit ocarina. I'll leave links to these on the website if you want to learn more about making your own. But this guy takes it to the next level. He's actually taking these carrots and he's playing a song with them.
Guess who's back again? Oh, they don't know.
So he's mixing it.
As soon as we walk in, show it up. Take your sip, do your dip, spend your money like money.
Now, he just overdubs himself. It's really neat. He makes a slide whistle out of this one. So if you watch, he's actually pulling the carrot in and out to make kind of like a trombone sort of thing. And then he's got like a saxophone here where you're covering individual holes. And so every sound that you hear here is something from a carrot.
Way too fresh, gotta blame it on Jesus. Hashtag blessed. I'm a dangerous man with some money.
Yeah, too much time. I forget what they call this thing. This is a really unique instrument, like a pipe organ, basically. And this guy, he feeds these this paper into it. And every time there's a hole punch, it plays different pipes. That's really neat. It's playing Michael Jackson's Smooth Criminal. You gotta wonder how they punch those cards. This guy's he's busking. I don't know where he's doing it. Someplace. Busking is when you sit out on the street and you play music, and people pay you money if they're generous. So he's just got a series of PVC pipes that are different lengths, and the length will dictate when he hits it with his sandal. Maybe you might know this song. And then the last one. These are, it's a choir from Harvard called, I think they're called Thud. But you maybe had these when you were a kid. They're called boomwhackers. It goes on. I'll leave links to all these videos on my website, or you can go to my playlist at Mr. Hare on YouTube, and you can see all these and more if you're interested. But I want to talk to you about standing waves here, especially in open and closed tubes. So what we're going to do when we're looking at open and closed tube resonators is the first thing, this is a closed tube. For a closed tube, the really thing that's really important is that you know that on the end of the open side, we have what's called an antinode. And you probably remember antinodes from when we were using last chapter with that drill and that string that would go around. So a transverse wave, the antinode is going up and down the most. And when this is a longitudinal wave, so these molecules are going in and out the most. So right here is an antinode. When you've got an open tube, when on the open side of a closed tube, you've got an antinode. Over on this side, you have a node. If you've got that wall there, that wall isn't allowing those molecules to go in and out. So as long as you have a node and an antinode for a closed tube, you're good to go. So what we've got here, this is what we call the fundamental. It's the lowest frequency that will work because I've got a node right here and I've got an antinode right here. This will work inside of here. So I could do a higher frequency, and you saw me blow that that 40 ounce a little bit earlier. So if I go higher frequency, this will work, but as long as I have a node on the closed end and an antinode on the open end, that's okay. Go a little higher still. The wave is getting more and more complicated, but what remains the same is that there's a node and an antinode, higher still. Higher frequencies are playing inside of this tube, and you'll see the wave gets more and more complicated up here, but you've got a node on one side and an antinode on the other. So if I go back down and I change this to an open tube, if this is an open tube, now this node over here changes to an antinode. The same kind of rules apply. I have an antinode on one end and an antinode on the other end. This is the lowest frequency, so you can see it's called the fundamental. So if I go a little bit higher, I get my first overtone, and this is antinode on the right, antinode on the left. It's legal. Keep going. I have antinodes on either end, no matter what I do. Let's go down and investigate these a little bit further. Let's look at a closed tube. So if I've got a closed tube, what I've got here, this piece of a wave, this is actually 1/4 of a whole wave. So if this was a whole wave, it would look like this from start to finish. And this is 1/4 of that. So this would be 1/4 of my wave. So the lowest note that will play on a closed tube is 1/4 of a wavelength. And then I go a little bit higher. So I go to my next one. And I look at this one. If you look at this, this is 3/4 of a wave because it's to the top, back down to the middle, and then down to the other side. I've got a node and I've got an antinode. And this is 1, 2, 3/4 of a wave. I'll go to my next one. Here I've got 1, 2, 3, 4, 5/4. And by now you might be noticing a pattern that's happening. I go to my next one. One, 2, 3, 4, 5, 6, 7/4. You can see that they're stepping up by 2/4 or 1/2 every single time. So this is my closed tube. Now what I'm going to do is I'm going to make it an open tube. So I'm going to have an antinode on both sides. Go back here, erase this. And let's talk about an open tube. My lowest one on an open tube. My lowest one here, this is 1/2 of a wavelength. Again, if I'm looking at a wave from here to here, start to finish, this is 1/2 of a wave. Now I'm going to write this really special, and you might start to see a pattern here. 1/2 of a wave. Go to my next higher one. This is 2/4, 3/4, 4/4. This is a whole wave. Go to my next highest one. This is going to be 1 1/2, 6/4. And the next one's going to be 8/4. So there are some similarities and there are some differences between open and closed tubes. The similarities are, in both cases, they're both stepping up by half a wavelength. From one resonance point to the next resonance point, it's always half of a wavelength each time. What's different about them is that the open tube starts at the odds. The open tube starts at even, so it's 2, 4, 6, 8, and the closed tube starts at the odds. So let me show you how I leverage these ideas. And the main ideas are this. Main idea number 1 is that if you have an open end, it has to have an antinode. If you've got a closed end, then you have to have a node, right? You're forced to have a node on the end that's closed. You're forced to have an antinode on the end that's open. And the other big idea is they always step up by half a wavelength. Now let me show you how I would do some problems related to this idea. Example number 1 says that there's a 290 Hertz tuning fork is played above an open tube of adjustable length. What's the spacing between resonance on the tube? Let me draw a picture of what's happening and we can go from there. So I've got a tube and it's open on both ends. And remember, with an open tube, you have to have an antinode. The air has to be able to go in and out freely on each end. So the shortest one that works on an open tube is this one right here. Right? Now, if I could make this tube longer, just extend the tube, I have to just make sure that there's another antinode on the other side. So my wave would then look like that. And when they talk about the spacing, this is the spacing. This is what they're looking for, that distance, that spacing. And you'll notice that the spacing is 1/2 of a wavelength. That's the key to this whole problem, knowing that if you could figure out the wavelength, which we can pretty easily, if you can figure out the wavelength, the spacing is just half of it. Velocity of sound is 343. Don't know the wavelength, but the frequency is 290. So when you take 343 divided by 290, you get 1.2 meters. So that means that the spacing is half of that, half of a wavelength. So the spacing is 0.60 meters. Let's take a look at our next example problem. It says it's the same setup, a 290 Hertz tuning fork, and you're playing it above a closed tube this time. What's the spacing between resonance on the tube? So in this case, I'll draw the picture. I've got a tube, except it's closed on this end, and then I draw the open end. The thing about a closed tube is you have to have a node here, and you have to have an antinode on the other end. So the shortest wave that will work, in this case, you've got a node and an antinode. And you remember that this is 1/4 of a wavelength. The next place that will resonate here is this. You just have to have another antinode on the other end. This tube is adjustable. You can go in and out with it. So again, just like the last time, this distance from here to here is what they're looking for. The spacing. And you'll note that exactly like the last time, this is half of a wavelength. So if we could just find the wavelength, turns out it's the exact same thing. 343. Our frequency is 290. So our wavelength equals 1.2 meters. The wavelength is half of that. So the spacing is half of that. So this spacing is going to be, again, 0.60 meters. And you'll remember that's what they shared in common. When we were doing this, the thing that was shared between them is that they always go up by half a wavelength. It doesn't matter if it's open, it doesn't matter if it's closed. And you're seeing that now in this problem when it asks for the spacing. Example number 3 says you got that same tuning fork and you're playing it above an open tube of adjustable length. Give the 3 shortest lengths that will resonate. So again, I'm going to start with my open tube, open on this end, open on this end. And remember, when you have an open tube, you have to have an antinode and an antinode. So here is the shortest tube that will work. My next tube is going to be this long, so it's going to be another half of a wavelength. My next tube is going to be this long, and it's another half of a wavelength. So what I'm going to do is I'm going to figure out how long is this. So then I would just say the tube is this long, twice that, or 3 times that length. Let's figure out that length. I'm going to use velocity is equal to wavelength times frequency. My velocity is 343 meters per second. My frequency is 290. Again, the wavelength comes out to be 1.2 meters. So this distance right here is half of a wavelength. So this distance is 0.3 meters. This distance from here to here, call it D2, that's going to be twice that, or 0.60 meters. This third distance, which is going to go from here all the way over to there, call it D3, that's going to tack on another 0.3, 0.90 meters. So the 3 wavelengths, or the 3 lengths of tube that will work for this are 0.3, 0.6, and 0.9. Pretty straightforward. It gets a little bit trickier when you have a closed tube, and that's what example number 4 is. You've got that exact same thing, except you're playing on a closed tube. So let me draw a closed tube. Now remember, the only difference is that you have a node here and an antinode there. So the shortest one that's going to work here is 1/4 of a wavelength. And remember from our whole equation, 343. I use 290 in all these so they could always be the same. But you might have different stuff every time. So 343 divided by 290, 1.2 meters. So this length is 1/4, right? This length right here is 1/4 of a wavelength. And since one wavelength is equal to 1.2 meters, 1/4 of that is going to be 0.3 meters. So that's your first place that this is going to resonate. Now, your next length, you have to go 1/2 of a wavelength, right? So if this is 0.3, 1/2 of a wavelength is 0.6. And then your next resonant place is another 1/2 a wavelength, and that's another 0.6. See how I'm leveraging the fact that resonant spacings are every 1/2 of a wavelength. So the first place, the first length that's going to work is 0.3 meters. The next one that's going to work, it's this length from here to here, and that's 0.9. Significant figures. My next one is going to be 1.5. I'm going to take this plus 0.6 plus 0.6 plus 0.3, and that's 1.5 meters. So this one's not so straightforward. You're not doubling it. You start out with 1/4, and then you go to 3/4 of a wavelength, then you go to 5/4 of a wavelength. So you could do the same thing. You could just take 1/4 of 1.2, 3/4 of 1.2, 5/4 of 1.2, and you'll get those numbers as well. Example 5. I believe this might be, yeah, this is my last example. What's the lowest 2 frequencies that will resonate in a soda bottle that's 30 centimeters long? So this problem is just a little bit different. They give you a forced distance, and now they're saying find the frequency. So you've got a soda bottle is going to be a closed tube. and you have to have a node here and an antinode here. So here's the lowest frequency that's going to work. This is 1/4 of a wavelength. And I know that this distance right here is 0.30 meters. Okay, so if 1/4 of a wavelength is equal to 0.3 meters, that means that one wavelength, you multiply both sides by 4 and you get 1.2 meters. Okay, so I could figure out what frequency is going to be played here using velocity is equal to wavelength times frequency. So my velocity is 343. My wavelength is 1.2, and I can find my frequency. My frequency turns out to be 286. And that's where that 290 came from. But this time I've got 3 significant figures, so the first frequency that will play, this is my lowest, my fundamental, this one right here, is 286 hertz. The next frequency that can play is 3/4 of a wavelength, right? I've got a node right there, and I've got an antinode right here. So this is going to be a little bit different. So in this case, 3/4 of a wavelength are going to be equal to 0.3 meters. So now to figure out what one wavelength is here, so a wavelength would be this long, like the distance from here to here is equal to a wavelength. So what I'm going to do is I'm going to multiply by 4/3. So I multiply 0.3 by 4, 1.2 divided by 3. So one wavelength in this case equals 0.4 meters. And that kind of makes sense. Do you see how this distance equals 0.4 meters? I get this out of the way. So now I could figure out my second frequency that plays. Velocity is equal to wavelength times frequency, 343. Wavelength in this case is 0.4 times the frequency f. So that frequency turns out to be 858. I know this took a little bit longer than you're used to, and I apologize. This is probably the most difficult conceptual stuff that you will deal with all of second semester. I really wanted to throw you a lot of examples just so you could have a lot to draw on no matter what they ask. So this is the idea of open and closed resonators. Remember, the big deal is if it's closed, you've got a node, and if it's open, you have an antinode. And if it's always stepping up by half of a wavelength, no matter what that you're doing, if it's open or closed.